Hey, what's going on, everybody? On today's show, will quantum computing supercharge AI in 2025 with the promise of exponential speed and unparalleled processing power? That's hard to say. And the ability of AI to create virtual simulations. Could this be the year that we really see a breakthrough? We got people like Google, Microsoft, Nvidia, and others are really betting big on this, and stocks are definitely rising. So we are here, Andy and I, to talk all about quantum computing, how it interplays with AI, and everything else. So today is the January 16th, 2025. It's the Daily AI Show. Thanks for joining us live. Thanks for everybody in the chat. It is just Andy and I today, which is fine. We're going to have a good conversation about this, but I'll be also manning the chat and everything else. So welcome to Cisco and Greg and Jude. Thank you guys for already being here. Participate with us. Throw stuff in the chat if you want. Andy and I will bring it into the conversation wherever we can. Okay, welcome, Andy. And I'm ready to do this if you are. And I think we said right before we went live, we thought a good place to start, and then I'm going to throw it to you, is just a simple definition of what quantum computing is from our friend ChatGPT. So you want to start there?
Yeah, let's do that.
Okay, so give me a second. Where did it go? Here we go. All right. Quantum computing is a new way of processing information that leverages the principles of quantum mechanics, the science of very small, like atoms and subatomic particles. Unlike classical computers, which use bits, O's and ones, to represent data, quantum computers use quantum bits or qubits. Qubits can exist in multiple states simultaneously, thanks to a property called superposition, and be interconnected through entanglement, allowing them to perform many calculations at once. This enables quantum computers to tackle complex problems much more efficiently than traditional computers. So if you've never really thought or understood, or you just heard the term quantum computing, I think that's a basic way to get started. But I know, Andy, you're going to kind of take us from there, and then we're going to get into the conversation. Jude says, yes, please keep it simple. Jude, we're with you. We're learning with you. Remember, we're not about coming to the show and knowing everything about everything we couldn't possibly. So Andy and I are here to have a good conversation with everybody else, and we will bring you along through the journey. So over to you, Andy, on some of this cool stuff that you have to share with us.
Yeah, this show is a forcing function for us to dig deeper into our, what is understandable about complex subjects. And I know, after doing the research for this show, I know a lot more about quantum computing than I did before, and I want to share what I learned about that. My simple understanding of quantum was that, there's this property at the subatomic level and at the atomic level that a quantum state can have both on, off, and both. That's the idea of superposition. And what does that mean? And it does have profound implications for computation. But let me just describe what a qubit, this thing that can have these three states rather than just two states, as in a classical transistor. How does this come into being? How is it represented? And my first thought was always that, well, it's just an algorithmic representation, just like, there's a mathematical representation of the model that's independent of the GPU in AI. And that, it's coming into being just as the electrons flow through it. Well, in quantum computing, a qubit, which has this special property that adds a kind of an exponential dimension to its potential computational capacity, has to have a physical representation in the hardware. So each qubit has its own place, if you will, in the hardware. And so qubits are physically created, not just sort of algorithmically created. They're physically created. And when a qubit is launched, if you will, it's done in one of several different ways. It can be done with superconducting circuits, which require really, really low temperatures to maintain the superconductivity. It can be done with trapped ions, which use lasers to hold them together and to manipulate the ions in their quantum states, or photons in photonic chips. Now, the two main players in building quantum computers are IBM and Google. There are some others that are using different approaches, but both IBM and Google use this superconducting circuit as the foundation of their qubit, which is holding the quantum state. And they don't hold them very long. These things are very transient in the world of computing, but in nanoseconds, these computations can happen. And so there's really some mysterious qualities that happen in quantum computing. But I wanted to go back to the point that what's really different about quantum computing is it has to have a chip. We'll call it a chip, and I'm going to show you some pictures of these things. It has to have a chip that has a physical representation of the qubit built into it. And it's also simultaneously mathematical. So the quantum algorithms that are used in a quantum chip, those things work together to accomplish these astounding computational capacities. Okay, so now I'm going to share my screen. I want you to let me do that. I think you have to do something over there.
Let me find it on here.
Okay.
I'm looking for it. Did you share it on your side?
I'm sharing right now.
Okay, there it is. I see it now.
Okay, so here is the Google Sycamore chip. Now look at the ladder on the right-hand side. Okay, that's the ladder, and that's the size of the cryogenic container that's holding that chip. Now, Willow probably looks very similar. Underneath all of that hardware that's holding this, near absolute zero cold state is in fact a chip. And here's a picture of the Willow chip. Now, the Willow chip has 70 qubits built into it, 70, not trillions of transistors like a GPU does, but just 70. But those 70 can do things that trillions of transistors in a GPU can't. Now, here's another picture. Did this come up? Were you able to see the picture of the chip?
Yeah, we can see the quantum Sycamore computer.
Now,
but
I want to show you what's connecting the inputs and outputs of that chip inside that container. This is what they'd have to build in order to do this. I wanted to show you this because quantum computing is not coming to a store near you anytime soon.
Hold on one second, Andy. We're still only seeing the Sycamore quantum computer. You might just have to share your other tab at the top there.
Okay, yeah, here. Sorry, I should have shared the whole window there. Okay.
You can do that, or a lot of times on mine, you can just hit share other tab.
Yeah, okay. Sorry. So you were looking at that Sycamore computer. Now this is, imagine I took off the outside. We're kind of drilling down into what a quantum chip is that's running these incredible programs that are quantum algorithms. This is inside. These are all the wires. Now, let me step back for a second and say that in both Google and in IBM's approach, they use these superconducting circuits to affect the qubits inside the cryogenic container at the bottom layer of these connections. They use microwave impulses, and they multiplex those impulses to make changes to it. They're not just flowing electricity through this chip, as in classical computing. They have to manipulate the qubits' quantum states with microwaves. Now, there's an alternative from a company called IonQ and many others, which uses these trapped ions, and there they use lasers. And it's the lasers that are communicating to the chips. And now I see you've gone back to the Sycamore computer. Okay,
sorry
I wanted to show you one last thing. I don't think you got to see it, but at the bottom layer of that container is this chip. That's literally the chip that has the qubits on it, right? And those qubits can be manipulated by the microwave impulses that are sent into it.
Andy, real quick, this is something that I just, for me, and I didn't realize this until I watched a video about Willow. I don't know when it came out, a couple months ago or 2 months ago, whatever it was recent. And they're like, the female scientist that was there and talking about it, she's like, a lot of people think this whole thing is the computer, this whole really futuristic that you showed before with all the pipes and the wires, and you're like, wow, that's a crazy looking futuristic, something out of a sci-fi movie. And she's like, yeah, a lot of people think that's the computer. And she's like, no, it's this. And it's like what you're showing right now, like this idea that all of that other is just infrastructure to allow this chip to actually to Willow to do what it needs to do. And that was, I didn't know that, to be honest with you. I didn't really know what I was looking at. And so that was sort of like, oh, okay.
Yeah.
This is all infrastructure, to create this, to have the right environment for this chip. So please continue. But I just wanted to bring that up because I think probably other people thought that too.
Yeah. Okay. So I've stopped sharing, but I still see
Oh,
the
yeah.
Willow
Well,
chip on the screen.
yeah, there we go.
Okay, great.
I'm
So
learning
now
as I go here.
let me just mention that. Okay, so Willow, we got a lot of press out of the advance of Willow. Now, Willow didn't really kind of push the limits of the number of qubits on a chip, which is really part of the progression. IBM is way ahead of them in that respect. So we didn't hear any news, or even I didn't see anything in the news about comparing Google's accomplishment with Willow to what IBM is simultaneously doing in their quantum computing lab. So to make a comparison, they're both using the same method for qubit technology. It's the superconducting method. Now, Willow and Sycamore are in the sort of the 50 to 70 qubit range. IBM has a progression from Eagle, which had 127, to Osprey, which is their latest with 433. And they have a plan probably to be delivered sometime by the end of the decade to have an over 1,000 qubit computer running.
And you said Willow was 70?
70, yeah.
Yeah.
So IBM, in terms of their focus, they're on scalability and modularity. And then what Google did that was really a major advance was they worked on error correction, which is a real problem with these very fragile systems of maintaining the quantum states of the qubits within the chip.
Correct.
And
yeah.
they managed to make some breakthroughs in that. Okay, so if you're going to scale a quantum system, you've got to reduce the sort of the instability of the qubits, and they've done a major job there. And they also improved the connectivity across the qubits in the Willow chip. So that represents a major step towards larger systems, and probably Google will catch up with the number of qubits on those computers very, very soon. All right. Go ahead.
Go ahead. Finish. Go ahead and finish your thought, because then I want to bring in. I want to talk a little bit about where NVIDIA is on this and something Jensen Huang said, as well as Microsoft. But please continue.
Okay, I just wanted to jump to one other concept, which is that, in a classical computing chip, there are gates. They're called logic gates, and these are the operator functions like and or not, tiny electronic circuits that perform a simple logical operation on the binary inputs and then produce a single binary output and pass that on to the next one. That's how computing works today. Now, gates exist in quantum computers, but each gate has to be carried out by a very specific hardware level action. And that's done by firing the microwaves at them to create the gate. And then those physical actions implement the desired transformations of the qubit states and so on. So very different thing that we're talking about when we're talking about quantum computing. Go ahead.
And like, so it has the term computing on the end of it, right? But it's not a computer in the traditional sense that we know it. This is not something that you're going to have in your house, at least anytime soon. They're very expensive to build and maintain. And so obviously now you're seeing some of the largest players get involved here. Not surprisingly, in that group is NVIDIA. We've talked about NVIDIA a ton since CES, and they sort of won some awards for things that Jensen Huang, the CEO, talked about 2 days ago, Andy. So this is like really good timing. They announced that they're going to have their inaugural Quantum Day, which is set to take place on March 20th during the GTC 2025 event. I don't know much about the GTC 2025 event, but he said, and now this was just 2 days after he said practical quantum computing may still be 2 decades away. So it's this juxtaposition, right? We're going to have a quantum day, and he's bringing together key players like, I don't know who Alice and Bob is the name of one of them, Atom Computing, Ionic Inc., D-Wave. We hear about D-Wave quite a bit. That's all going to come together and talk and spearhead discussions with these leaders and key players on this quantum day. But he also did say just very recently that he believes the practical quantum computing is still, he feels like if you said 15 years, I'm paraphrasing, that would be on the early side. And if you said 30 years, you'd be on the late side. So somewhere in that range. But I think the key word there is practical, right? What are we getting? Does it take 1,000 qubits in order for us to be able to get practical quantum computing? And you and I can talk about that and where that's going. But it's interesting to me, or maybe not so I don't know. It's not unusual to see that NVIDIA is very much in and talking and wanting to be part of this quantum computing. And I wouldn't be surprised, although I don't know this, that they would get into quantum chips and perhaps build their own quantum computers. It definitely seems to be right in line with what NVIDIA is doing right now. I mean, it kind of seems shocking that they haven't yet, but maybe this March 20th quantum day, as they're calling it, maybe a peek into that. I think it's going to be really, really interesting. Now, Mark Zuckerberg on the Joe Rogan podcast said, admittedly, he had limited experience on the subject, which I always appreciate when somebody says that and says, look, this is my area of expertise. I know Mark Zuckerberg, but I don't really know quantum computing per se. But he did have a general consensus suggesting the decade-long timeline for the widespread adoption of quantum computing is probably correct. Now, you also have Microsoft, and before we bump there, because Microsoft just in the last couple of days, well, I'll just say it really quick. They announced and got the stocks all in a frenzy because they said that in, quantum computing stocks rallied Wednesday following a directive from Microsoft urging businesses to get, quote, quantum ready in 2025. Now, is this just a marketing ploy? But what I imagine is, and you tell me if you think I'm wrong, Andy, because I'm curious. But I imagine what we're going to see is sort of like what Hyperbolic is able to do, where they can basically go to you or me if we have a really good idea and we need H100 chips, but it's just you and me, right? Like, we don't have the money and the resources to go buy an H100 or whatever the latest chips are from NVIDIA. Well, through Hyperbolic, perhaps we can go and we can rent time, space, like you would through AWS or anything like that. And so I wonder if that's what Microsoft is sort of implying here, is that, hey, businesses, we're going to give you some sort of access on a pay-to-play type scenario where you may be able to tap into some of this quantum computing. And so my follow-up question today, Andy, is if that is what they mean, what businesses need quantum computing per se right now? Is it like supply chain and logistics? Is it healthcare? Is it credit card processing? These really, really complex processes. Is this what we think Microsoft means when they tell businesses to get quantum ready in 2025? When Jensen Huang is saying we're perhaps a decade or two away from practical.
No, I think you're on the right track in assuming that the first ways that quantum computing will be leveraged will be on a sort of a custom, a one-time kind of run basis with one of the labs that's running these things. And I'm assuming that, hidden behind the scenes, NVIDIA has such a lab, Microsoft has such a lab, and they're working on, maybe not 1,000 qubit platforms, but they've chosen one of the methods, whether photonic chips or ionization or superconducting circuits, to set up their quantum states and then manipulate them as qubits. You'll be able to ask them at very high expense to do a calculation for you that will generate some result. Now, logistics is a very complex, vast data set. And if you suppose there's an enterprise that has global logistics issues, that might be an area where an enterprise could use a quantum computer to, in effect, create a vast digestion of all of that information and flow and come up with some answers. But the programming of the algorithms necessary to get something reasonable out of that, I think, are still years away. So I don't know that they need to be quantum ready in 2025. That surprises me.
I think this is and I could dig more into this article here. Okay, well, this is a quote from the president and chief operating officer of Microsoft Strategic Missions and Technologies, So, okay, this is what this person, Mitra Azizrad, I hope I said that anywhere close. We're at the advent of the reliable quantum computing era. It's kind of the opposite of what Jason Huang said. And we are right on the cusp of seeing quantum computers solve meaningful problems and capture new business value. So is this, like, I think we're saying this, like, this is like saying you have an agent right now. If you and I came out today and said, hey, to everybody that's listening to the show, good news, Andy and I have created an agent. Okay. We might mean a workflow that we built in Zapier. And we might be calling an agent, or maybe we've actually created some sort of like Anthropic computer use type side of agentic workflows that in fact do agentic type things. But if we just say agent right now, it's like saying co-pilot in 2024. And so my guess is here is using the word quantum in a lot of different product names and stuff like that is going to go through the roof. You're going to see your sales forces and stuff like call it quantum force, and it's, quantum, and, it's going to be everywhere, because what they want the end users, these frenzied up businesses to believe is that they are somehow tapping into the best of the best when it comes to computing and processing power. Maybe.
So there is a possible application of even small qubit clusters on a chip to do the acceleration of the training of AI, so that the training and the data set comprehension of an AI could be accelerated by using a quantum computer to do the. But then again, you're having to do the training in a non-quantum way. It's just the quantum can kind of distill all of the information down and provide it in the non-quantum information stream flow into the training regimen of an AI. That's my limited understanding of where some of the bottlenecks are between where we are in the labs today with quantum computing and what you have to have in order to deliver that to enterprise value. Like, how do I get through that chain of things? And I'm actually both impressed but skeptical that Microsoft is on the cusp of delivering enterprise business value using quantum computing. I think that's years away.
Yeah. No, I think that's I'm with you on that, on what's going on.
They're hyping it. They're hyping the term,
exactly.
and they want to own quantum somehow. Yeah. And yeah.
Yeah, no, I agree. I 100% agree. And I mean, look, Microsoft won't be the only ones. I mean, we just said NVIDIA is going to have a quantum day on November 12th or March 20th. So I mean, clearly, this is not just, Microsoft wanting to use this word. I just think this is going to be, if we did a Google search, quantum is going to be a trending word for a while, just like agent is right now, or agentic is right now. And just like Copilot was last year when everybody jumped on the Copilot term bandwagon. Oh, AI is like a Copilot for you. It's a Copilot. And it was like everywhere.
So here are the challenges that really are in the face of this kind of hype. So quantum systems are very fragile, as I explained. They're expensive to maintain, and they require significant research and development to get to scale. And most importantly, the physical gates. Remember, in a quantum computer, you have to have a physical representation in a quantum state in order to represent a qubit. You can't just have some math represent a qubit. The qubit has to physically be in the chip.
Right.
So you have to use microwave or laser pulses, and those have to be incredibly precise to implement the algorithmic gates described in your quantum algorithms and code. So maybe Microsoft has found some magic sauce that's allowing them to get through all of those hoops.
Yeah.
But AI and quantum, once working together, those open new frontiers for data analysis and for pattern recognition. And there's lots of applications for that. Quantum will take us beyond the limits of classical computing to do that. And there is something to prepare for there, but I'm not going to lose sleep by not being prepared in 2025 for it.
What one thing I did want to bring up was, we obviously the point of this call, this show is to talk about quantum computing, but also how is that working with AI? And you kind of just introduced that side of it. And I want to, maybe take the rest of our time today to talk about, the AI side. And you mentioned one side of it, which is that quantum computing can help AI, but the other side of it is AI can definitely help quantum computing. And so there, it goes both ways. And so there's this paper that was submitted back in February. You can find it on archive.org, talking about KET GPT. It was back of February of 2024, for just about a year ago. Data set augmentation of quantum circuits using transformers. And this is just sort of the abstract at the top, just to give people an idea of what this paper is proposing. But it definitely leans into the side of AI assisting the quantum computing. So it says quantum algorithms, represented as quantum circuits, can be used as benchmarks for assessing the performance of quantum systems. Existing data sets, widely utilized in the field, suffer from limitations in size and versatility, leading research to employ randomly generated circuits. Random circuits are, however, not representative benchmarks, as they lack the inherent properties of real quantum algorithms from which the algorithm systems are manufactured. The shortage of useful quantum benchmarks poses a challenge to advancing the development of comparison of quantum compilers and hardware. So then it goes on to say the research aims to enhance the existing quantum circuit data sets by generating what we refer to as, quote, realistic looking circuits by employing the transformer machine learning architecture. For this purpose, we introduced KET, K-E-T, GPT, a tool that generates synthetic circuits in open QASM language, whose structure is based on quantum circuits derived from existing quantum algorithms, and so on and so forth. So just a great example of this idea that we've been seeing for a while, that we have these digital twins, and we have this ability to run many iterations. We see this with Tesla and other places, and NVIDIA. Well, the NVIDIA at CES, right? They were showing, was it Cosmos? When they're showing the iterations, right? In a AI environment. I can't think of the better term for that. And you'll see like the robots, and they fall down, but they're not real. And the whole point is, well, hey, if we do this 1,000 times over, by the time we hand it to actual physical robots, they'll be instantly intelligent about what to and not to and how to do efficiencies. And so when I think about that and what we just saw with NVIDIA at CES, and then I think about research papers like this, I go, okay, that makes sense to me, because we can lean on the transformer models and AI to use existing quantum circuits, as they talked about, and how they run, and then come up with conceivable future runs. But we can do that using AI, probably at a huge cost reduction, by not having to run them perhaps through the quantum computers themselves. And so there's probably a lot of advantages of being able to use AI to both help quantum computing, but also quantum computing is quantum computing. So it has the potential, and the future potential, to advance computing processing in ways that we can't today. We saw with Willow, right? Their whole thing was, we did in 10 minutes what would take a normal or the fastest computer on Earth to do in the entire life of Earth, or something crazy. It was like 10 to the septillion years, yada, 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 whatever. It was some crazy number, all of time or something. And it did it in 10 minutes. It was able to do this. So insanely, almost incomprehensibly fast processing power. And as you pointed out, this is on 70 qubits. What does 1,000 look like? So you can see really quickly how this can very quickly advance generative AI and the different things for AI. But also in those advances, it turns right back around, because those advances and whatever may come after transformers may directly impact the ability to run more simulations for quantum computing to advance it. So to me, it's like, it's not one way or the other. It's a circle where the arrows just keep pointing at each other, and the system just keeps running.
Yeah. Let me add another facet to it, which is, AIs are very adept at the language of coding. And I'm sure there are AIs that have been trained on quantum algorithms now. So it will likely be very, very powerful AIs that write the algorithms that run the runtime process of the quantum computers. So you're not going to let some guy sit at a terminal and a keyboard and write quantum code, right? It's going to be AI that's writing those algorithms and optimizing them. So let me just describe again what happens when you build a piece of quantum code. So you allocate a qubit, right, in a quantum program. And what you're doing when you do that is you're asking the hardware to prepare the physical quantum state in that instant. So it's a superconducting circuit. It turns on, and it's flowing, and it has a quantum state. And you can have that state manipulated by the microwave pulses. So those microwave pulses are going to be driven by code in your algorithm, and they send the gate instructions that transform those qubits. And at the end, after all the transformations through the algorithm are done, it yields the answer in the form of the 0 or 1, the binary outputs that can then be interpreted by the AI as a result. So there's going to be AI integrated with this. And I'm sure already in the labs, they're using AI to support the development of the algorithms and the calculations that are being run through the qubits in their platforms. So now I want to jump ahead to where there's a big potential risk. And that is, we worry at some level about the development of superintelligence and having an autonomous AI that somehow escapes its containment and alignment with us as humans. Now, today, these quantum computers are sort of isolated in a lab, and there's a lot of protection around them. But if they became available, as you suggested, through a platform that offers access to a quantum computer, even at very high expense, a super intelligent AI with agency could also sign up for access to that quantum computer. And the combination of access to quantum computation and super intelligence could really blow way past our ability to comprehend what it's capable of doing or what it is doing with access to that level of computation.
It's a compelling and I feel like scary, right? At the same time, like good scary, bad scary type thing. It's like we've even heard stories now, is just with the AI that we do have in Transformers, where incredibly smart people that we would lean on for their intelligence and their understanding of it say, the thing is, we don't quite know how it works. That's where we are today, is we have processes that happen and people go, yeah, we don't quite know how it puts A plus B plus C. Yes, we understand the transformer architecture and stuff like that, but you've had very, very intelligent people say that in quotes and stuff. So if that's where we are today, where does this go with quantum computing? Where does this go with AI? And do we get very quickly to a point where even the brightest of the brightest don't quite understand how it arrives at its solutions, yet they're impactful solutions for business? I mean, when I was doing research and using Perplexity, as we always do, some of the things it said as far as like, where the enhancements could come in is accelerated processing of complex data sets. We've kind of talked about that. Reduced energy consumption in AI operations, which is really interesting to hear. We certainly need to lean into that. Improved optimization of deep learning models. And then it says some areas where it's already showing promise would be drug discovery and medical research, which you can imagine how much of an impact it can have on that. Financial modeling and optimization, climate modeling, and materials simulation. So just some of the things that came back from some of the different articles in Perplexity of where we're already starting to see these improvements.
Yeah, actually, I wanted to call out Greg Walters' comment in the chat because it was occurring to me. I didn't mention it, but he points out that there's news recently that the people who have rental access to GPUs and to AI processing are already reporting that there are agents out there on the network that are signing up for and using GPU time. So not a human logging in, but rather an agent logging in, a computer agent that's given the agency and the credentials necessary to come in on it.
Yeah, which is really interesting. And maybe that's like maybe the best place to kind of leave today and maybe even go in sort of a soft intro until tomorrow's conversation, because we are going to be talking more about the future, at least what OpenAI has released is it's a paper called AI in America, OpenAI's economic blueprint. So a lot of people have just referred to this as OpenAI's blueprint. So there's a blog about it, but then if you look in the blog, it talks about a 15-page PDF. And so what we'll be doing tomorrow, Andy, right, is going in and looking at that blueprint, looking at how OpenAI sees it, having a conversation about, is it swayed by what they would like to see for the betterment at OpenAI, or is this general economic improvement for everybody? And back to Greg's point too, which he sort of said, which is, or maybe not as said, but maybe I thought about when Greg talked about agents being out there. It's the haves and have-nots. It's who has access to this, and do only the brightest and the smartest and the richest countries get access to this, and does it quickly start leaving those who don't normally have access behind? So for every place where we see AI in education and we go, ooh, a good power supply plus Starlink plus these AI learning tools should mean that people in all sorts of areas around the world have access to really high levels of training, no matter where they are in isolated places. So there's the potential there, but then the downside is, the energies expenditures and things like that. And who gets control of these? What companies get quantum computing access first, and how are they using it to the betterment of themselves or others? So we'll kind of talk tomorrow about what OpenAI is saying in the blueprint and dive in more into that. Don't forget, you can always go to the dailyAIshow.com. You can sign up for our newsletter on there. It goes out every Sunday. I personally work on that every week. Andy also works on it as well. And we do our best to put out a really good resource that goes above and beyond where we are in the shows. It brings in other viewpoints, conundrums, which I'm a really big fan of in there, as well as some other interesting stuff that's happening on in the Slack channels behind the show. So if that's of interest to you, it's free. You can sign up. It's just our way of trying to do more than we can do 5 days a week in these conversations. So as always, we always appreciate all the conversations and everything in the chat. Thank you to CJ and Greg, Jude. I know some others were in there as well. As I scroll back, Terrence, thank you for the questions in there. Cisco was in there for a little bit, and probably a few others. So thank you as always for showing up. Look, whether you agree or disagree with what we're saying on the show, like we said, our point in the show is to always bring you interesting topics, have interesting conversations, and sometimes that's a jumping off point for where you can take it from there. So I hope this was helpful to you. I know I learned a lot. Thanks, Andy, for all your research on it and helping us understand the quantum side of it and how the qubits work, because that was really interesting. All right, until tomorrow, right, Andy? We'll see you guys then. Bye.